It is my pleasure to introduce our second keynote speaker, Professor Lulu Qian. So Lulu joined Shuki's Paradise Group in 2009 and became a professor of bioengineering at Caltech in 2013. Since then, Lulu did groundbreaking work on DNA-based neural network, as Yasser referred to, DNA self-assembly, and swarm molecular robots, among others. She is a recipient of numerous awards, including the Feynman Prize for Excellence in Teaching. As you know, that's one of the coolest awards at Caltech. And she is also the advisor to my daughter, who was an undergrad at Caltech a few years ago. So welcome, Professor Lulu Qian.
Thank you, Qian. So when I think of Shuki, I think of a huge tree that grows everything. Every one of us here today represents a leaf. Shuki gave us the inspiration, energy, and wisdom to become someone unique. As a mentor, he ran with us and then let us fly. So today, we come back to celebrate Shuki and to remember the special journey that we had with him. So I would like to share with you 7 stories about some of the most important things that I have learned from Shuki. The first is the beauty of simplicity. Shuki convinced me that all complex phenomena must have simple explanations. And the only way to master complexity is to build on simple yet powerful principles. So Shuki accepted me into his lab in 2009 when I was a postdoc doing weird molecular engineering stuff that didn't quite make sense. I wanted to build logic circuits out of DNA molecules. And one day, I was in Shuki's office drawing some diagrams like this on his whiteboard. So in order to process molecular information, signals that are intrinsically analog, I relaxed the binary representation of on and off states to accommodate some noise and signal decay. And with that, I designed a set of DNA molecules that each perform the function of summation, thresholding, and amplification. So together, they were expected to compute whether the sum of the 2 inputs is above or below 0.6. And when both inputs are off, the maximum signal is 0.4, was the definition of off state, right? So that means the output should be 0. When at least one input is on, the minimum signal is 0.8, and thus the output should be 1. A nice feature about this molecular logic gate design is that the same set of molecules you see here could be used to implement an AND gate by just changing the threshold value from 0.6 to 1.2. Because in this case, when at most one input is on, the sum should not exceed 1.2, and thus the output should be 0. Otherwise, the sum should be at least 1.6, and thus the output should be 1. So Shuki looked at my design and asked, could you use the same set of molecules to build a neural network with linear threshold gates? Okay, that was the first time that I heard about a linear threshold gate. So Shuki explained to me the function and pointed out the similarity to the logic gate function. The general purpose linear threshold gate has a variable threshold, which was already possible in my design just by changing the concentration of a threshold molecule. But unlike a logic gate, the linear threshold gate computes the weighted sum of all inputs, where each input has a variable weight. So I left that meeting feeling both confused and excited. To answer Shuki's question, I started reading about linear threshold gates from Shuki's lecture slides. And I learned that a linear threshold circuit can be actually are more efficient, compute more efficiently for all functions that are and or not circuit computes by using a smaller circuit or with fewer layers. And that was very interesting to me because as an experimentalist, I was struggling to build a DNA circuit in a test tube that had just a few logic gates. So the possibility of doing more computation with fewer molecules gave me some hope. But more than that, Shuki's question opened a new world of neural computation to me. And I started asking myself, what does it mean to be smart? Well, we first need to recognize a situation correctly before making a good decision. For example, it is not necessary to run away from a cat and not a good idea to hug a tiger. Similarly, recognizing a situation is also important in a molecular environment. For example, a nanorobot made of DNA was built to recognize a disease cell based on the biomarkers on the cell surface and open the barrel structure so that the antibody loaded inside can be given to the disease cell, but not to the normal cell. However, recognizing things can be tricky, right? If this is not challenging enough for you, how about the dogs? Anyone has an answer? Come on, brains. I heard 6. I heard 8. I heard 9. Wow, we have different answers. See, we cannot even agree. It's 8 because a checkerboard pattern, right? Recognizing things in a molecular environment can be even trickier. For example, there are over 1,000 aroma compounds in coffee. And it takes a very complex olfactory neural circuit to tell the difference between good and not so good coffee. Inspired by how the brain processes information, the principles of neural computation have been developed over the past 80 years, forming the foundation of modern machine learning. So after reading about linear threshold circuits and other models of neural computation, I began to think about the possibility that one day we'll be able to use molecular circuits to make everything smarter. For example, we could have a smart vaccine that lives in our body, remembering every earlier encounters with pathogens, and trigger our immune system to fight against the future pathogens for all similar diseases. Or a smart Band-Aid that we could remember what irritates our skin and adapt its material properties to keep us feel perfectly comfortable all the time. So my lab now has a full line for research to understand the principles of neural computation in engineered molecular systems, and it all began from Shuki's question. And the first paper that we published together on building a DNA-based neural network. Indeed, Shuki was right. A linear threshold gate can be implemented with the same type of molecules that are used for a logic gate. However, a challenge was that in this implementation, the value of each weight was represented by the concentration of a weight molecule, which means negative weights should not be possible. To address that, we used a technique called dual-rail logic, where each input is replaced by a pair of inputs representing logic off and on value separately. And then similarly, each weight is replaced by a pair of weights representing the positive and negative value separately. With this implementation, with this representation, each linear threshold gate can then be replaced by a pair of gates with positive weights only, that producing a pair of dual-rail outputs. And once the design principles were figured out, we went ahead and built a hot field network that performed molecular pattern recognition. So as you all know, Shuki always emphasized having fun doing research. And indeed, we had a lot of fun designing a game and playing it with the DNA neural network. So the game is called Read Your Mind. And to play, you will think of a scientist. Out of 4 given options, I will ask you 4 questions, and you will answer yes, no, or I don't know. But you will not tell the answer to me, but instead to a DNA hot field network in a test tube. For each question, if your answer is yes, you will add 1 specific DNA strand to the test tube, and a different strand if the answer is no, or adding nothing if the answer is I don't know. Suppose your answer is, the scientist I'm thinking of was born in the 20th century but was not a mathematician. So the communication is executed by adding 2 DNA strands to the test tube, which indicate the 3rd bit being 1 and the 4th bit being 0. Then the fluorescence signal starts to go up that you can measure on a plate reader. After 8 hours, we can now read the output. So here's how we read it. The solid purple trajectory is off, and the dotted purple trajectory is on, indicating that the first bit is computed as 0. Similarly, the solid green trajectory is on, and the dotted green trajectory is off, indicating the second bit is computed to be 1. So this is the DNA neural network's way of saying, the scientist you're thinking of didn't study neural networks and was British. So I guess she is Rosalind Franklin. Okay, that's game. And building on this work with Shuki, 7 years later, a graduate student in my lab, Kevin Cherry, scaled up DNA neural networks to process 9 classes of 100-bit molecular information, encoding the MNIST handwritten digits. And this newer generation of DNA neural networks used a simple competitive function called winner-take-all, where the linear threshold function requires each neuron to have its own threshold. The winner-take-all function requires all neurons to compete with each other, and the only one that turns on is the one with the largest weighted sum of the inputs. An important feature of the winner-take-all circuits is that negative weights are not necessary, as only the relative values matter in selecting a winner, which means we don't need the dual rail technique anymore, and now we can have fewer molecules. Importantly, winner-take-all circuits are actually more powerful than linear threshold circuits, even with just positive weights. So to build a DNA-based winner-take-all neural network, we first translate the abstract mathematical function into a set of chemical reactions where each variable is represented by the concentration of a chemical species. Next, we design a set of DNA molecules to implement each of the chemical reactions. And these are all short single and double strands on the scale of microRNA molecules. When a specific set of input strands are added to the test tube, they trigger a cascade of reactions and generate an output strand which indicates which memory the input is most similar to. And this is illustrated by the classification of handwritten digits encoded in 100 unique DNA strands. And in real-world applications, these molecular handwritings could represent any information of interest, such as a disease profile, and the classification results could lead to any desired action, such as a therapeutic response. So I hope this work shows that I have learned well from Shuki about seeking simplicity to master complexity, and I have continued to use it in my own research group. And building on this work, we have now started to explore more sophisticated behaviors, such as learning. So in silico learning produces a DNA neural network with fixed memories, acting like a hardwired processor. In contrast, in vitro learning enables the liquid system itself to form memories in response to examples of molecular inputs during a training phase, acting like an adaptive memory device. When composed together with a processor, This integrated system can provide learned input-output function applied to a subsequent testing phase. And we successfully demonstrated 100-bit pattern classification after 3 distinct training processes, providing compelling experimental evidence that molecular systems can learn to perform complex information processing tasks. It has been hypothesized that learning played a significant role in the early evolution of life by accelerating evolution through the Baldwin effect, which alters the shape of the fitness landscape. In supervised learning, however, a teacher is needed to label training examples with desired responses, which is incompatible with the early development of life. So now the challenge is to enable chemical systems to learn in an unsupervised fashion. And in such a regime, the system will be exposed to information in their molecular environment, but without guidance on responses. And they must use this information alone to enhance the capability on processing similar information in the future. So in this continuously learning process, there are no distinct phases of training and testing. The system constantly learns and refines its classification decisions. And thus, a critical requirement is a power supply that recharges the system while it learns. To do that, we developed a strategy that uses heat as a universal energy source for powering a wide range of molecular circuits, like ATP for biological systems and electricity for electromechanical machines. The key idea for heat-powered reusable molecular circuits is that they operate at room temperature, consuming energy stored in kinetic traps to process information, and recharge at a higher temperature, converting heat to energy restored in kinetic traps. We showed that the same set of DNA molecules in the test tube can repeatedly process varying input patterns and reset successfully for many rounds of computation. I hope one day we could catch up with the success of electrical and computer engineering. Like electronic stations for cars, we could build heat stations for molecules where they diffuse to and recharge themselves. That's a dream. Okay, now the second thing that I've learned from Shuki is that to be a good teacher, we must convince the students to learn for joy, not for grade. When I started teaching my own class at Caltech in 2015, I worked very hard to achieve that. So the class I developed is about programmable molecular systems. The goal is for students to design and build their own DNA circuits and self-assembled DNA nanostructures. This is what I say to the students in the first lecture. You might have had the following experience while doing research. Everything works until it stops working. I prefer a different experience, where everything don't quite work. But we collect understandings like jigsaw pieces until one day we figure out how the pieces come together, leading to a beautiful ending. The second journey can be quite a bit longer, but also quite a bit more meaningful than the first. So in this class, my lectures include detective stories about debugging DNA circuits and nanostructures. And you will be graded not by how many things you get to work, but by how many jigsaw puzzles that you collect. I also adopted Shuki's strategy about giving everyone an A. So I showed the statistics in the first lecture to convince the students that it is not hard to get an A in this class, and this is intentional. So every year, I set up 2 design competitions in the class, and this is one example. Students were asked to design an interesting logic circuit using up to 6 logic gates with a few other constraints about the number of inputs, outputs, gate types, and layers. So here's the winning design by Chris Sachuk in spring 2015, voted by all students in the class. He designed a logic circuit that computes 2 one-dimensional cellular automata transition rules. I know some of you know this really well. Each rule can be illustrated by a set of 8 input and output combinations, where 0 and 1 are represented with white and black pixels here. And L, C, and R correspond to the left, center, and right input pixels. The output pixel corresponds to the updated state of the center pixel determined by all 3 inputs. So if we start with a string of binary numbers 0, 0, 0, 1, 0, 0, 0 arranged in a one-dimensional grid, and apply rule 110 to compute the second row of pixels, for example, 0, 0, 0 yields 0, 0, 0, 1 yields 1, 0, 1, 0 yields 1, 1, 0, 0 yields 0, etc. And now the first generation outputs will be produced, which then become inputs for the next row. If we continue doing this for 8 generations, an image of a dog will emerge. If we start with the same initial configuration, but apply rule 124, a mirror image dog will emerge. A fun fact, rule 110 is famously known as Turing universal, which means it can compute any desired functions. So when Chris presented this design in the class, he told a story of when rule 124 meets rule 110. And this story was very memorable, and that's possibly a good reason that he won the design competition. Using a molecular compiler that I developed earlier, the student-designed logic circuit was automatically converted to a DNA circuit design. When the students tried to build this DNA circuit in the lab, however, they found out that it did not compute correctly when constructed using unpurified molecules. So we didn't purify the molecules because the purification procedure is both time-consuming and labor-intensive, and not suitable for students with no prior background. If DNA circuits could be built from unpurified components, the experimental procedure would be much simpler, making DNA circuits more accessible to researchers with diverse backgrounds. And motivated by this challenge, the students developed a systematic procedure for constructing DNA circuits using unpurified components. Thanks to their work, it is now possible to follow a flowchart that defines the main issues one might encounter and proceed with suggested solutions. Okay, let there be dogs. The ideal logic circuit behavior corresponds to images of black dogs with white backgrounds. The DNA circuit yielded less contrast between the dogs and their backgrounds, but the patterns are still clearly recognizable. So every year, students surprise me with very creative designs, and we had so much fun building stuff like this in the wet lab. So as mentioned, 14 years after Shuki received the Feynman Prize for Excellent Teaching, I was honored with the same prize. The third thing that I've learned from Shuki is about mentoring. When I started my own lab in 2013, my biggest struggle was to be a good mentor. I'm a solitary person, and I don't have much people skills. So working closely with someone was the last thing that I had naturally wanted. But every time I felt hopeless, I reminded myself about what Shuki said. Run with them, then let them fly. In fact, the first time that I practiced to run with someone was the experience working with Dan Wilhelm. With Shuki, Dan proved a remarkably simple yet beautiful theorem that the probability of an arbitrary binary fraction can be realized with a single type of switch that has 1/2 probability for connecting the input terminal to the output terminal. And then Hongchao and Holin further proved that arbitrary rational probability can be realized with a single type of split switch that connects one input terminal to each of the 2 output terminals with equal probability. As an example of demonstrating the power of stochastic behaviors in molecular systems, I worked with Dan and Shuki to make these probabilistic switching circuits in DNA. And I want to admit that at first, I felt that I was doing everything wrong when I was trying to teach them how to do experiments. And Shuki showed me incredible patience and encouraged me to keep going. It took a few years, but eventually, we successfully demonstrated both feed-forward and feedback circuits generating output with desired probability using an exceptionally simple molecular building block. The fourth thing that I learned from Shuki is about scientific communication. Attending Shuki's group meetings was a particularly enjoyable experience for me because that was one of the few places I can actually understand what the theorists are talking about. Shuki's secret for giving a great presentation is to explain one truth deeply and earn the audience trust for the rest. Every group member learned to do this well. However, explaining technical details to a broad audience is often hard, so we must be creative. Here's the seesaw analogy that I came up with to explain a DNA reaction mechanism. I used it in my talks, but I was at first uncomfortable using it in the paper. And Shuki said, "You must do it." So now you see this somewhat ridiculous figure unmatching the serious style of the journal. The reaction mechanism is for signal amplification in a DNA circuit. When an input strand catalytically converts a fuel to an output strand. Imagine that the output molecule is initially sitting on the right side of a seesaw, and the input and fuel molecules are wandering around. When the input molecule jumps onto the left side of the seesaw, it pushes off the output molecule. Then the fuel molecule pushes off the input molecule in a similar way, and at this point, the fuel and the output molecules have exchanged their places, while the input molecule is still free to jump onto another seesaw. That's the mechanism of signal amplification. Now let's imagine a playground of seesaws. Every seesaw exchanges the activity of molecules on the two sides. Every molecule can play on two different seesaws. Such a playground is a network connected by the flow of signal molecules. So I'm glad I inherited some of Shuki's whimsical style for scientific communication because the name seesaw circuit is now well known in our community. I love Shuki's career advice. Find the intersection of your talents and your passion. I have now given this advice to many of my own students and postdocs. It can be painful to watch someone keep trying to do things they're just not good at. Or to hear someone saying, "I was a code monkey this summer. I analyzed a ton of data, but I'm not sure what they mean." So I keep reminding myself that my job as a mentor is to help people find this intersection where they can thrive. I was once facing a difficult decision about life. I wasn't sure if it was a good idea to be with Eric. I told Shuki I was afraid to forever live in Eric's shadow. For everything I do, people would think that I could only do it because of Eric's help. Shuki said, "The right partner matters more than everything else." Then he added, "Things will change. Eric will one day live in your shadow." I laughed when Shuki said that, and I was deeply moved by his confidence in me. So now Eric and I have been together for over 15 years, and we have Shuki to thank for. The last but not least, I admire Shuki so much for his philosophy about happiness is an attitude. The day passes either way. Why not choose to be happy? Whenever I get stressed out about a deadline, and you know there are a lot of them, or on the edge of being depressed about something, I think of Shuki's philosophy. It is very powerful. It helped me remain as happy as I could possibly be. Needless to say, Shuki is a brilliant mathematician, scientist, engineer, technologist, and most importantly, a brilliant mentor. The inspiration, energy, and wisdom that he gave to all of us will live on. There's nothing I could really say that will properly address my deep gratitude. So let me just say, thank you, Shuki.